आदर्श शिंदे, अंकिता, Chandrasekhar.
Yes, sir.
Okay. Roll number 5. Roll number 6. Roll number 6. 7, 8, 9, 10, 11, 12, 13, 14, 15.
Sir, 12.
Okay.
12.
Okay. 16, 17, 18, 19, 20, 21.
Present, sir.
Okay. 22, 23, 24.
Yes, sir.
Okay. 25, 26, 27, 28.
Present, sir.
Okay. 29, 30.
Present, sir.
Okay. 31, 32, 33, 34, 35.
Present, sir.
30. Okay. 36. Joslino, Soham, Atiya, Shweta.
Present, sir.
Okay. Deepa, Hanumant.
Yes, sir.
Okay. Ilyas.
Present, sir.
Right. Prajwal, Prathamesh K, Karthik, Sohel, Rohit, Sridhar Patil. Sridhar Patil is there. Vishal, Sampath.
Yes, sir.
Okay. Anybody else joined? Chandru Pattar.
Srishek.
Abhishek, sir.
Pardon? Abhishek. Okay.
Srishek.
Srishel. Okay.
Prajwal Mali, sir.
Okay. 1 minute. Just a minute. Prajwal Mali. Okay. Srishel. Matyari.
Sir, Deepa.
Deepa. Okay. Prajwal Mali, Srishel. Anybody else? Abhishek.
Abhishek.
Okay. Anybody else? Okay. You are able to see the screen? Are you able to see the screen?
Yes, sir.
Okay. Yesterday I discussed the various types of classifications of amplifiers, that is class A, class B, class AB, class C, and class D amplifiers, right? So let us first study the first type, that is class A amplifier. It is called as series fed class A amplifier or direct fed class A amplifier. Here it is called a series fed or direct fed because the transformer is not used here and the input is applied directly to the base. So it is called as series fed or direct fed class A amplifier. If a transformer is used in the circuit, then it is called as transformer coupled class A amplifier. Okay. So this is series fed or direct fed class A amplifier in which the input is applied to the base terminal directly. So it is series fed or direct fed class A amplifier. In this series fed class A amplifier, it is similar to the fixed bias circuit. Right, in module 1, you have studied the various types of biasing circuits, that is fixed bias circuit, emitter bias circuit, voltage divider bias circuit, collector to base bias circuit, right? Emitter bias circuit, all these biasing circuits you have studied in module 1. This is nothing but the fixed bias circuit. Series fed class A amplifier is the fixed bias circuit. In the fixed bias circuit, the RB is connected between base to collector. Resistance RB is connected between base to collector of the transistor. This is the transistor. It is NPN transistor because the arrow is pointing away from the this emitter terminal. So it is NPN transistor. Okay, and the RB resistance is connected between base terminal and the collector terminal. The RC resistance or the load resistance is connected to the collector terminal. So this such a circuit is called as the fixed bias circuit, and the emitter terminal is grounded. This is called as fixed bias circuit. The fixed bias circuit, resistance RB is connected between base to collector. RC resistance is connected to the collector terminal. Emitter terminal is grounded, and the input signal is applied to the base. So such a circuit is called as series fed class A amplifier, or it is nothing but the fixed bias circuit. It is a fixed bias circuit, but it is meant to handle the large signal voltages. The input signal magnitude is larger, right? The previous fixed bias circuit, what we studied in module 1, it is for the small signal voltages that are applied. They are in terms of millivolts or microvolts, a few volts, but here the voltage input is large, right? So such in large signals are handled by this power transistor. The power transistor is meant to handle large input signal voltages. This is a difference between the fixed bias circuit that we have studied in module 1 and the fixed bias circuit or the series fed class A amplifier that we are studying in this module. Okay, in module 1, whatever you have studied, it is the same fixed bias circuit, but the input signal, it is smaller. In this module, the power amplifier module, whatever we are studying, the input signal is of larger magnitude, and this larger input signal magnitude is handled by the power transistor. It is handled by the power transistor or the transistor which we are using in the power amplifier circuits. Okay, the base current that is flowing is IB, the collector current is IC, right? The capacitor that is connected to the base terminal is C1. This is coupling capacitor. This is called as coupling capacitor. Okay, it is a large signal amplifier which is handling the signals in the range of volts. That is, it is nothing but the power transistor that is meant to handle the power in terms of tens of watts. The power handling capacity of the transistor, it is in terms of tens of watts, or the output power provided by this transistor, it is in terms of tens of watts, right? The output power is more than the input power. That is why it is called as power amplifier. The power output of this circuit is more than the power input to the circuit, and hence it is called as the power amplifier. But the power efficiency is less. If we compare class A power amplifier with other power amplifier circuits, the efficiency is less. That is, comparatively the output power is less in class A amplifier as compared to the power output in the other class amplifier circuits, and hence the power efficiency in class A amplifier is less. The current gain of the transistor, it is denoted by beta. Current gain of the transistor is denoted by beta. It is nothing but the ratio of the output current to the input current. The current gain beta is given by output current divided by input current. Output current is IC, the collector current. Input current is IB, the base current. Therefore IC by IB gives the current gain, that is beta of the transistor or of the transistor circuit. Okay, this beta of the transistor in the class A amplifier circuits is less than 100. The beta, the current gain of the transistor that is used in the class A amplifier is less than 100. Overall amplifier circuit using power transistor, that is what it is. It is meant to handle large power or the current while not providing much voltage gain. It is meant to handle larger currents or the larger voltage or the larger power, right? And the output is in tens of watts, right? But the voltage gain is less. The voltage gain of the class A amplifier is less. Voltage gain, it is the ratio of the output voltage to the input voltage. The ratio of output voltage to the input voltage is called as gain of the circuit or gain of the amplifiers. The ratio of output voltage to input voltage, that is output voltage divided by input voltage, gives the gain of the circuit. This gain of the circuit is less for the class A amplifier circuits. Next, let us move on to the DC bias operation of the series fed class A amplifier circuits. Now the DC bias means we are considering the VCC. We are considering this VCC DC voltage applied. When we are applying the DC voltage, right, that time whatever the current and the voltages are available in the circuit, so based on that we are analyzing the circuit. Based on that we are analyzing the circuit. Okay. So when we are performing the DC analysis, the VCC is present, right? We are considering the VCC. So we are applying the KVL to the input path of the circuit. Now, what is the input path of the circuit? The input path here is from VCC through RB, then VBE to ground. This is called as input portion or input path of the circuit. It is from VCC through RB, then through VBE. This is base to emitter voltage, VBE, and emitter to ground. This is called as the input path or the input portion of the circuit. Okay, input path or input portion of the circuit. If we apply Kirchhoff's voltage law, KVL, right? What is KVL? KVL is the sum of the voltages in a closed loop, that is, yeah, the total sum of the KVL, Kirchhoff's voltage law. If you apply the KVL to the circuit, the sum of the total voltages in a loop is equal to 0. Okay, so that is we are applying the Kirchhoff's voltage law here, right, to this input portion. Okay, to this input portion. If we apply the KVL here, we get VCC. Let us apply the KVL here. So the equation will be VCC, the DC voltage, VCC minus what we'll get. This is positive negative, that is VCC. Okay, starts from VCC. Their current is flowing positive to negative minus IBRB. Current entering is positive, current leaving is negative. Okay, so it is positive to negative. Current is flowing from positive to negative. Decrease in energy. It is flowing from positive to negative. It is decrease in energy. That is minus IBRB. Okay, VCC, then positive, negative. Current entering positive, current leaving negative. Right. So it is going from positive to negative minus IBRB. minus IBRB, VCC minus IBRB minus IBRB, okay, minus IBRB minus, what about the base to emitter voltage? VBE, it is positive here, it is negative here, current entering positive, current leaving negative. Therefore, from positive to negative, the voltage from positive to negative, it is decrease in energy, therefore it is taken as negative. If it is from negative to positive, it is increase in energy, it is taken as positive. Okay, so positive to negative, it is decrease in energy, therefore it is taken as negative. So minus VBE minus VBE minus VBE base to emitter voltage is equal to 0. So in a loop, the total sum of voltages is equal to 0. Okay, this is, we are applying the KVL. Now this equation we are rearranging to obtain the value of IB. Okay, we are rearranging the equation to obtain the value of IB. Therefore, IB is given by IB is equal to IBRB. Let's write it. IBRB is equal to VCC minus VBE. VCC minus VBE. Okay. Or IB is equal to, or IB is equal to, or IB is equal to VCC minus VBE divided by RB. VCC minus IBRB minus VB is equal to 0. I am taking minus IBRB to the RHS. It will be plus IBRB. That is equal to VCC minus VBE, or IB is equal to VCC minus VB divided by RB. Okay, this is the equation for the base current. Right now, VBE we know that it is 0.7 volts. Okay, it is 0.7 volts for the silicon transistor. Therefore, it is VCC. It is VCC minus 0.7 volts, this divided by RB, This is the equation for the base current. Okay. That is, IB is equal to VCC minus VBE divided by RB. VCC minus 0.7 volts, VBE is 0.7 volts, it is fixed for silicon transistor, that divided by RB. Okay. The collector current, take it as equation 1. The collector current, we know that it is given by IC is equal to beta into IB. The collector current is always given by the equation IC is equal to the current gain beta times the base current. IC is equal to beta into IB. Okay, take it as equation 2. Collector to emitter voltage. Next, let us write the equation for collector to emitter voltage. What is the collector to emitter voltage? If we consider this collector to emitter, this is emitter base collector clockwise, emitter base collector. Okay, that is collector to emitter voltage. Between the collector terminal to emitter terminal, the voltage is VCE, that is collector to emitter voltage. Now, how to find this collector to emitter voltage? If you want to find this collector to emitter voltage or the output voltage, this is the output voltage between collector to emitter, then again we have to apply the KVL now to the output path of the circuit. We have to apply the KVL to the output portion or to the output path of the circuit. What is the output path of the circuit? VCC through RC, VCE, then emitter to ground. Which is the output portion? VCC through RC, VCE, then emitter to ground. This is the output portion of the circuit. Okay. Now let us apply the KVL to the output path or to the output portion of the circuit. And what we get if we apply the KVL to the output portion of the circuit, we get the equation will be VCC minus IC RC VCC okay, VCC minus ICRC, current entering positive, current leaving negative. It is positive to negative minus ICRC. Then current entering positive, current leaving negative, minus VCE is equal to 0. Minus VCE is equal to 0. Okay, minus VCE is equal to 0. right? Now let us rearrange the equation for VCE. Therefore, VCE will be equal to VCC minus ICRC minus ICRC. VCE is equal to VCC minus ICRC. I am taking minus VCE to the RHS. It will become plus VCE. Therefore, VC is equal to VCC minus ICRC. This is the equation for the collector to emitter voltage. Okay. Now we got the equation for collector to emitter voltage using the KVL. Take it as equation 3. Now this is the graph which is the output characteristics of the circuit or the output characteristics of the transistor here. Right? The output characteristics is nothing but the plot of or the graph of the collector current to collector to emitter voltage. It is a graph of collector current to collector to emitter voltage. That is, it is a graph of collector current to collector to emitter voltage. IC versus VCE for different values of base current. Right? For the graph of the collector current versus the collector to emitter voltage for different fixed values of base current, that is nothing but the output characteristics, is also called as the collector characteristics. Output characteristics or the collector characteristics. Right? Now for different values of the base current, suppose say this is IB is equal to 5 microampere, then as I increase VCE, the IB is increasing, IC is increasing, and I further increase VCE, it is remaining almost constant. IC is remaining almost constant. Similarly, for the next one, IB, let us say it is 10 microampere. First, when VCE is less, IC is also less, right? As I am increasing VCE, the IC will increase, and when I further increase VCE, the IC will remain almost constant. So like this, we are getting different curves for the different values of the base current. That is the graph of IC versus VCE. Okay. Now here we are getting these curves, right? Now once we get these curves, next we have to find the bias point or the operating point or the quiescent point. This is called as Q point or the quiescent point or operating point, and it is also called as the bias point. Right? Now to find this bias point, we have to use the output voltage equation of the transistor, which is the output voltage equation VCE is equal to VCC minus ICRC. Because in this equation we have VCE and also we have IC. Okay. Therefore, VC is equal to VCC minus ICRC equation has to be used in order to determine this Q point or the operating point. Now let us find the operating point here. Note that students, here on the x-axis it is VCE, the IC is 0, collector current is 0 on the x-axis, that is VCE, and if we take on the y-axis, that is IC, VCE will be 0. Is it not? On the x-axis it is VCE, therefore IC will be 0. On the y-axis it is IC, therefore VCE, the collector to emitter voltage, will be 0 on the y-axis. Right? Now let us substitute this IC equal to 0 and VCE equal to 0 in this equation. That is, VC is equal to VCC minus ICRC. Let us do that. Now in this equation, we have already got this equation. In this equation, what I will do is, first I will substitute for x-axis, right? On x-axis, what is 0? It is VCE, IC is 0. So if I take IC equal to 0, then what I get? If I substitute IC equal to 0 in this equation, right? IC is 0 means IC RC will be 0. Product of IC into RC will be 0. Therefore, VCE will be equal to VCC. VC is equal to VCC. I am substituting IC is equal to 0. If I substitute IC is equal to 0, IC RC will be 0 or VCE will be equal to VCC. That is, here I am getting VCE is equal to VCC. Can see here VCE, this is VCC. Okay, this point I got right on the x-axis when I substitute IC equal to 0. Now what is the point that I will get on the y-axis if I substitute VCE is equal to 0? Right, let us see that. If I substitute If I substitute VCE is equal to 0, VCE is equal to 0 here in this equation, what will be the equation? If I substitute VCE is equal to 0, then the equation will be VCC minus IC is equal to 0, or right, IC will be equal to VCC this divided by RC, this divided by RC. VCC minus ICRC is equal to 0, VCE is 0, or IC is equal to VCC divided by RC, VCC divided by RC, right? That is the equation that we are getting here, that it is IC is equal to VCC by RC. That is the point on the y-axis. Now, whatever point we are getting on the y-axis and the x-axis, join these 2 points, right? Join the point on the y-axis with the point on the x-axis. If we join these 2 points, then wherever this is called as a load line, that is the point VCC by RC and the point VCC, this line is called as the load line or the DC load line. Wherever this DC load line cuts the IB curve, wherever it cuts the base current curve, that is called as the Q point or the quiescent point or the operating point. Okay, wherever the DC load line cuts the base current curve, that point is called as the Q point or the quiescent point or the operating point of the circuit or the bias point of the circuit. Okay, now we got the Q point or the operating point, it is here. Okay, now for this Q point, the corresponding value of IC, it is called as ICQ, and the corresponding value of the VCE, it is called as VCEQ. That means it is the collector current at the operating point and the collector to emitter voltage at the operating point. Okay, ICQ and VCEQ. Okay. This is the collector characteristics, what I showed just now. The intersection of the IB curve with the DC load line, it determines the Q point or operating point, is also called as a quiescent point, right? The quiescent point values, that is the values of IB, IC and VCE, are determined by the equations 1, 2 and 3. These 3 equations, that is IB is equal to VCC minus VBE by RB, IC is equal to beta IB, and VCE is equal to VCC minus ICRC, determine the quiescent point, that is Q point values, that is base current value, collector current value and the collector to emitter voltage. If the DC bias collector current is 1/2 the signal swing, that is if it is in between 0 to VCC by RC, right? If the DC current, the collector current, if it is in between 0 to VCC by RC, then the swing is nothing but it is the range of the positive to negative signal, right? Suppose say the positive half cycle is plus 5 volts, negative half cycle is minus 5 volts, then the range between plus 5 volts to minus 5 volts, right? So plus 5 volts minus of minus 5 volts, that is 10 volts. That is called as the signal swing. Swing of the signal. Swing of the signal means the range between the positive peak and the negative peak of the signal is called as the swing of the signal. Okay, so if the collector current, if it is in between 0 and the power supply voltage, right? If it is in between 0 and this VCC by RC, in between these two, right? Then the signal swing, the output signal will be having the maximum voltages, right? Because it is at the operating point Q. I told in the yesterday's class that if the signal is operated at the Q point, this Q point is in the middle portion of the characteristic curve. If the signal is operated, if the transistor is operated at the Q point, then the amplification will be large. The amplification will be large, right? That is the advantage of operating the transistor at the Q point. That means what? The signal amplitude, output signal amplitude will be larger if the transistor is operated at this Q point. Okay. If the quiescent collector to emitter voltage is set at 1/2 the possible supply voltage, the largest voltage swing will be possible. That is, if the transistor is operated in between 0 to VCC by RC, then the collector current will be maximum, ICQ will be maximum. And if the transistor is operated between 0 to VCC, then the collector to emitter voltage will be maximum. Collector to emitter voltage will be maximum. Okay, because it is operated at the operating point, the values are set in such a way that the output current we'll get is maximum and the output voltage is also maximum. Okay. Next, let us see the AC operation of the signal. Okay. First, we saw the DC operation. Next is the AC operation. That is, if we are applying the AC input signal, if we are applying the AC input signal to the circuit, right, then what will be the output current? What will be the output voltage? Now, when I apply the AC input signal to the base of the transistor, when I apply the AC input signal to the base of the transistor, right, then what will happen? I get the base current. The base current starts to flow, right? When the base current starts to flow, then I also get the collector current because IC is equal to beta into IB. So also the collector current flows and I get the collector to emitter voltage. Now, if I increase the input signal, if I increase the input signal, the base current increases. As the base current increases, the collector current also increases and the collector to emitter voltage also increases. Is it not? If I increase this input signal, the base current increases, the input current increases. As the input current increases, the output current must increase because IC is equal to beta into IB. The output current or the collector current increases, and then the collector to emitter voltage also increases. Right? Now, if we look into these graphs, that is the graph of IC versus VCE, right? This is the curve, characteristic curve, output characteristic curves, right? For the various values of IB base current. This is the DC load line, which is intersecting VCC by RC and VCC, right? And it is forming the Q point wherever it intersects the base current curves, right? Now, here, are you following here, students? Any doubts up till now? Are you following? Any doubts up till now? Yes, please. Any questions up till now? Students, are you following? Are you following here? Surya Banu?
Yes, sir, following.
Following, right? Okay, right. Shweta?
Yes, sir.
Following? Followed up till now? Any difficulty up till now?
No, sir.
Yes? Okay. Deepa? Deepa?
Yes, sir, following.
Following? Okay. Sampath Kumar? Sampath?
Yes, sir. Following.
Following? Any difficulty up till here?
No, sir.
Following, right?
Yes, sir.
Any problem in understanding?
No, sir. No, sir.
Okay, fine. Sanket? Sanket? Hanumant? Hanumant? Hanumant Patil? Okay. Now here, how to plot these signals, right? That we have to understand. See, this is the characteristic curve. Here we are getting the different base current curves, correct? IB1, suppose if I take this as IB2, IB3, IB4, the base current curves, right? Now from this, wherever it is intersecting the load line, these base current curves, from there I am starting, that is my input signal, because the input signal is the base signal, the signal which is applied to the base terminal. Is it not? If you look into this circuit, the signal which is applied to the base terminal, it is the input signal. The signal which is applied to the base terminal is the input signal. Okay, it is IB, correct? So I am drawing this input signal. I will get the input signal from the wherever the DC load line is intersecting the characteristic curves, IB curves, right? From this Q point, I am taking as the reference line, the reference, right? From there I am starting, I am drawing the input signal, that is the IB signal, input signal, the base current or the input signal that is applied to the base, right? Now this signal, input signal, will result in, or it will produce the output current and the output voltage, correct? It will produce the output current and the output voltage. Now where is the output current? It is here, IC is here, collector current, is it not? Therefore if I take this here, this is from this point I'm extending this, then this reference line also I'm extending, and the bottom line I am extending here. So therefore this will give me the collector current. If I draw it like this, the sine waveform, the AC signal, right, that will give me the collector current, because on this line I have the collector current, output current. Following? Then if I take on this horizontal axis VCE, it is nothing but the output voltage, VCE, collector to emitter voltage. Now how to draw this VCE? See here, I am marking certain points on this input signal A, B, C, D, E. Right? The points I am marking is A, B, C, D, E. Okay. So this is how I have to mark these points on the collector to emitter voltage to get the VCE. Now this A will, this lines I'm extending, the reference line, this is the reference line, this is the bottom line. Okay, this will be the this is the top line, this will become the bottom line. So this is the bottom line, this will become the top line. Okay, now this is A, so this A will come here. Try to understand here. This is A, so this A point will come here. Then this is B, this B will come here. This is C, so this C will come here. This is in the middle line, so this is C is coming here. Then this is D, so just I am extending this and I am putting it here. This is D, and this is point E, which is in the middle line, so that I am putting it here. Okay, I am marking it here, E. So this will give me the output voltage. The output voltage swing, that is whatever input signal I'm applying, from that input signal I'm drawing the output current IC and the output voltage VCE. Okay, so this is how we have to draw the output current, collector current, right, and the collector to emitter voltage, output voltage, given the input signal. Okay, first we have to draw the input signal. From the input signal we have to extend the lines, reference line, top line, bottom line, and draw the output current IC and the output voltage VCE. Clear here, students? Then, so as I told, if the base current increases, the collector current also increases, the collector to emitter voltage also increases. Now what is the limit at which the collector current will increase? Right? There should be certain limit. Am I right? Now how much is the limit till which the collector current will increase if the input signal is increasing? The collector current will increase between 0 and VCC, that is the limit. Okay, so between this 0 and VCC by RC, this point, and between this point and this point, the collector current will go on increasing, right? And similarly, the collector to emitter voltage VCE will increase between this 0 and this VCC, that is in between the load line only. Okay, the maximum is limited by the load line, right? This load line, whatever we have drawn, that will limit the maximum output current and the maximum collector to emitter voltage. So the maximum collector current is in between 0 and VCC by RC. This point is VCC by RC, and the maximum collector to emitter voltage is in between 0 and VCC. Okay, so like this we will be getting. So if we see here it is drawn on the next graph, right? It is the same as the previous one, but with the increased magnitude of the input signal, increased magnitude of the output current, and the increased magnitude of the output collector to emitter voltage. Okay, this is the current swing, output current swing between positive and negative peak, the range. Then this is the output voltage swing, VCE, and here we are having the input signal swing, that is whatever we are drawing from the base current curves, the reference line, the top line, bottom line. Then we are drawing the input signal. From the input signal we are getting the collector current signal, right? We are extending this line, reference line, we are getting this line, and the top line we are extending, the bottom line we are extending, and just drawing the AC signal that will give the collector current. Similarly, if we mark the points A, B, C, D, E, just as I discussed just now, then we'll be getting the points, same points A, B, C, D, E, like this for the collector to emitter voltage. Okay. When an input AC signal is applied to the amplifier, the output will vary from its DC bias operating voltage and current. So when we are applying the AC input signal, the output current and the output voltage will vary from the bias point, from the Q point. This is in between, it is the Q point here, right? In the middle, exact middle, it is a Q point. From this point, the collector current and the collector to emitter voltage will vary, they will change. A small input signal as shown in above figure will cause the base current to vary above and below the DC bias point. That's what I told. If you are applying a small input signal, the output current is also small, the output voltage is also small. But as you go on increasing the input signal, the collector current will also increase and the collector to emitter voltage will also increase, which will then cause the collector current output to vary from the DC bias point as well as the collector emitter voltage to vary around the Q point. As the input signal is made larger, the output will change around the DC bias point, around the Q point, until the current or the voltage reaches a limiting condition. Limiting condition means maximum condition. So the maximum is the collector current will vary between 0 and VCC by RC. The collector to emitter voltage will vary between 0 and VCC. For this, the current, this limiting condition is 0 current and the VCC by RC, higher limit. For collector to emitter voltage, it is 0 volts and VCC. Right? Then let us consider the power considerations. What is the input power that is applied? DC power. First, we'll consider the DC power. Then we will move on to the AC power and the RMS power. The power which is applied to the amplifier is provided by the supply voltage. Whatever this VCC we are applying, to the circuit, that will provide the DC power to the circuit. Okay. So this DC power to the circuit is given by the product of V and I. Is it not? What is the power? The power is product of voltage and the current. You have studied this. Am I right? Power is the product of voltage and the current. Power is equal to V into I. That is VCC into the collector current, that is ICQ. That at the operating point, VCC into ICQ, that is collector current at the operating point, that gives the DC power that is applied to the circuit. That is nothing but the DC power that is applied to the circuit. With no input signal, the DC current drawn is the collector bias current ICQ. If you are not applying any input signal, right, initially we are not applying any input signal, then the DC current is nothing but the collector current is flowing into the transistor. And there is a collector current, it is at the operating point, it is ICQ. The product of these two will give the DC power. Even with AC signal applied, the average current remains the same. Even if the AC signal is applied, even if we are applying the AC input signal here to the circuit, the average current remains the same because it is at the operating point that we have considered. So the average current remains the same. If you look into this graph, right? So this is the collector current. It is exactly in the middle. So it is the average current. Yes or no? It is the average current. It is exactly in the middle portion. That is at the Q point. Where is the Q point? It is exactly in the middle of the characteristic curves. That is, it is the average current. So even if the input signal is applied, the average current remains the same, and hence the input power to the circuit remains the same. That is VCC into ICQ. Hence, is the power, that is the output voltage and the current which are changing around the Q point, that will give the AC power that is delivered to this load, right? RC, the AC power delivered to the load when the AC input signal is applied. And the AC input signal is applied, we'll be getting the AC output power because of the output voltage and the output current that are varying around the operating point, and that AC power is delivered to the load RC. This RC is a load here, it is a load resistance, correct? That AC power is delivered to the load. The signal AC signal VI causes base current to vary around the DC bias current and the collector current. That's what I told. That is, the AC signal VI, as it changes, the base current changes, and as the base current changes, the collector current and the collector to emitter voltage also change. The AC input signal results in AC current and AC voltage signals. The larger the input signal, the larger is the output swing up to the maximum set by the circuit. So it may be current, maximum current, that is in between 0 and VCC by RC, and the maximum voltage, it is between 0 and VCC. Okay, that is, it is set by the maximum limit for the any of the circuits. The AC power delivered to the load can be expressed in number of ways. Okay, so whatever AC power is delivered to the load, that is RC resistance, that can be expressed in a number of ways. Okay, that we will take up in the next class. That is what is the power efficiency of the class A amplifier, and what are the various equations for the RMS power, that AC power of the series fed class A amplifier, that we will discuss in the next class. Okay, in today's class, students, we discussed starting with the series fed class A amplifier, right? Series fed class A amplifier, it is nothing but the fixed bias circuit, right? It is a fixed bias circuit, but it is handling large input signals. It is handling large input signal voltages, and that is, it is done using the power transistor. So the power transistor provides the output of few tens of watts, right? It is meant to handle large power. The power handling capacity of the power transistor is larger. Okay, beta of the transistor is less than 100. Current gain, it is the ratio of the collector current to base current. The gain is less here, that is the ratio of output voltage to input voltage is less for class A amplifier. Then the base current equation is given by applying the KVL to the input portion of the circuit, that is IB is equal to VCC minus VBE by RB, IC is equal to beta into IB, and VCE is equal to this. We will get by applying the Kirchhoff's voltage law to the output path, that is VCE is equal to VCC minus IC RC. Then we also studied the output characteristic curve or the collector characteristic curve, that is a plot of IC versus VCE for various values of base current. Wherever the load line, how we are getting the load line? When we substitute IC equal to 0 in the equation, VC is equal to VCC minus ICRC, we get that VC is equal to VCC, and in the same equation, if we substitute VCE is equal to 0, we get IC is equal to VCC by RC. If we join these 2 points, that is one on the y-axis and another on the x-axis, and the line that is joining, it is called as the DC load line. Wherever this DC load line intersects the base current curve, that is called as the Q point. Okay, and this is the Q point, which is exactly in the middle. That Q point, even we are getting Q points wherever this load line is intersecting for the other base current curves, but the Q point, which is exactly in the middle, that produces larger gain, or that produces larger amplification. Okay, then we studied the various characteristics or features, that is, as we are applying the input signal, as we increase the input signal, the collector current also increases and the collector to emitter voltage also increases. And how to plot the graphs? First we are drawing the input signal, we are extending these reference lines, right? And then we'll get the collector current curve, and if we take ABCDE points, we'll be getting the collector to emitter voltage curve. Okay, then this graph shows as the collector current, as the input signal is increasing, the collector current also increases, the collector to emitter voltage also increases, but it is within the limits of, that is, the collector current is within the limit of, it increases within the range, right? There is certain limit for increase of the collector current and the collector voltage. What is the limit for the collector current to increase? It is increasing only between 0 volts and VCC by RC. That is the maximum. It will not go beyond that. And the collector to emitter voltage, it is in between 0 volts and VCC. That is the maximum range it can increase. It will not go beyond these DC load line points. Okay, that is the maximum limit. Then we studied the AC operation and the DC operation of the series fed class A amplifier, right? Then we took up the power. That is when we are applying the DC voltage VCC, right? The collector current flows, IC flows. The product of VCC and ICQ, that gives the DC power input to the circuit. Okay. Then similarly, if you want to find the AC power, when we are applying the AC input signal, whatever is the collector to emitter voltage and the collector current, because of that, the power delivered to the load, that is RC, that is nothing but the AC power. Okay. So we'll discuss about the AC power and the RMS power, that is power efficiency equations of class A amplifier in the next class. Okay. Any difficulty here, students? Any difficulty here? Srishal? Abhishek?
Yes, sir.
Any difficulty, Abhishek? Followed today's class?
Yes, sir. No, sir.
Followed any difficulty, any problem in understanding?
No difficult, sir.
Okay, fine. Vishal Vasulkar. Sridhar Patil. Prajwal Mali.
Yes, sir.
Any
Yes, sir.
difficulty, Prajwal? Followed in today's concepts?
Yes, sir. Difficulty is no, sir.
Okay, fine. Deepa.
Yes, sir.
Clear with the concepts that we discussed in today's class? Okay.
Sir, we all clear.
Okay, fine. Shweta.
No, sir.
Clear what all we discussed in today's class?
Yes, sir.
Okay. Any problem in understanding, Shweta?
No, sir.
Okay. Manjunath Meligeri. Suraya Banu. Shubham Bekwadkar. Sanket. Sania. Ramesh. Chandrasekhar.
Yes, sir. Sir, clear, sir. All clear, sir.
Clear? Good.
Yes, sir.
Okay. Then in the next class, we will take up the RMS power equations derivation and the power efficiency derivation of the class A amplifier, and we'll start with the next amplifier. Okay. Thank you.